Okay, I welcome you all on my computer. So let us start the second session of higher order ordinary differential equations. This is the second session of higher order ordinary differential equations. So let us revise the first lecture, what we have discussed. At the end of the first session, we ended the session with capital F of D into y equal to Rx, where what is capital F of D? This was the polynomial in terms of D, and D is nothing but the derivative operator. Rx is the right hand side. To solve this differential equation, we have complementary function. We consider right hand side with 0, f of d into y equal to 0. Then we have auxiliary equation, which gives us the complementary solution. And on the other side, we have particular integral. The solution of particular integral gives us the particular solution. So to find the particular solution, we make the subject y. So y is equal to 1 upon f of d into rx. Our today's goal is how do we find the complementary solution. And then we have the general solution is ycx plus ypx, that is the sum of these two solutions. This becomes the solution of the given differential equation. So let us discuss the complementary solution. How do we find the complementary solution? We start with these three examples. Y double dash plus y dash minus 6y equal to 0. The second example is y double dash minus 10y dash plus 25y equal to 0. And the third one is y double dash minus 4y dash plus 13y equal to 0. You may observe that all these three equations are having second order. These are linears. Why these are linears? Because they are in the linear format. Right hand side is 0. So these are homogeneous equations, and the coefficients of the derivative term are constant. So these are the second order linear homogeneous differential equations with constant coefficients. Okay, now let us discuss how do we find the complementary solution. We shall discuss these three examples parallelly. Y double dash plus y dash minus 6y equal to 0, the first example. The second one is this, y double dash minus 10y dash plus 25y equal to 0. And the third example is y double dash minus 4y dash plus 13y equal to 0. So let us solve all these three examples. So look at here, y double dash can be represented y d square y that we have discussed yesterday. Y dash has representation dy, and this is minus 6y equal to 0. We take y common from the left hand side, so it is d square plus d minus 6 into y equal to 0. Now here we have two cases, either the bracket quantity is 0 or y is 0. But when y is 0, the system has no physical meaning, right? I mean y equal to 0 always satisfy this equation. The derivative of 0 is 0, the second derivative of is 0, so 0 plus 0 minus 6 into 0 is always equal to 0. But we are interested in if y is not equal to 0, then what happen? So when y is not equal to 0, we have d square plus d minus 6 equal to 0. This is a polynomial having degree 2, quadratic polynomial this is. Let us factorize this. So it gives us d plus 3, d minus 2 equal to 0. We are not going to discuss the factorization of polynomial here. You have nice practice at school level, that's why. So we have two values of d. One is minus 3 and another one is 2. For this example, this is now can I write direct d square y minus 10d plus 25y equal to 0. We take y common, y is not equal to 0. So d square minus 10d plus 25 equal to 0. Right, let us be fast a little bit. So this is the auxiliary equation, d square minus 10d plus 25 equal to 0. So it has factors d minus 5 square equal to 0. So it has two roots. This is the quantity d minus 5, again d minus 5. So it has two roots, 5 and 5. As we know that nth order polynomial has and roots, right? This is second degree polynomial, so it has roots -3 and 2. This has the roots 5 and 5. This equation, it is d square minus 4d plus 13 equal to 0. This is the auxiliary equation of this differential equation. Okay, how do you factorize this? You can think. You have a few seconds. Can you find the factors of this? This is quadratic polynomial, and you know how do we solve this thing. This is minus b. Let us compare with x square plus bx plus c. So minus of b is minus of minus 4, that is 4, plus or minus square root of b square minus 4ac. So this is 4 square minus 4, a is 1 and c is 13. Divide by 2 times a. Right, you are familiar with this quantity. It gives us this solution. 2 will be cancelled out here. So it is 2 plus 3i and 2 minus 3i. So all these three differential equations or these three auxiliary equation having two roots here, minus 3 and 2, 5 and 5, 2 plus 3i and 2 minus 3. I am very much interested in the nature of these roots. See, look at here, minus 3 and 2 both are real numbers and distinct. They are not equal. These are real numbers and equal, 5 and 5, the same roots we have. And these are the complex roots, right? So the nature of the solution depends on the nature of the roots. So here we have three cases. Case 1, when we have two roots, the two roots which are unequal. In the case 2, we have two roots which are equal. And in the third case, we have complex roots. So let us discuss case 1, when the roots are distinct and real. Then the solution format is this. ycx is equal to c1 into e raised to, this m1 will be here, m1x, plus c2 into e raised to m2x. This we have to memorize. The second case, when m1 and m2 are equal and real, then ycx is this, c1 e raised to m1x. Again, e raised to m1x, right? m1 equal to m2 here. But see, here I wrote some other quantity, extra quantity is x. If I don't write x here, then it is only single quantity, e raised to m1x, e raised to m1x, right? So to make these two quantities linearly independent, I multiply by x here. The concept of linearly independent we may discuss in one lecture. Case 3, when the roots are complex. Suppose m1 is alpha plus I beta and m2 is alpha minus I beta. Alpha is the real part and beta is the complex part. So the root solution ycx is this, e raised to alpha x, c1 into cos beta x plus c2 into sin beta x. Okay, so we divide the roots into these three natures, the distinct root, equal roots, and the roots are complex. Again I repeat, when the distinct roots, then we have c1 e raised to m1x plus c2 e raised to m2x. When equal roots, then it is c1 e raised to m1x plus c2x e raised to m1x. In the next example, this case will be more clear. ycx e raised to alpha x, so the real part becomes the power of exponential e raised to alpha x, and the imaginary part will be in the trigonometric function c1 cos beta x plus c2 sin beta x. In all these three cases, c1 and c2 are real constants. So now let us discuss the particular example. Y double dash plus y dash minus 6y equal to 0. This was the example which we already discussed. This example has two roots, minus 3 and 2. So minus 3 and 2 are distinct. So the solution is c1 e raised to minus 3x plus c2 e raised to 2x. The second example was this, y double dash minus 10y dash plus 25y. We have already discussed that it has equal roots 5 and 5. So for equal roots, we apply case number 2. So it will be c1 e raised to 5x plus c2x e raised to 5x. If you want, you can take e raised to 5x common. The third case, third example, y double dash minus 4y dash plus 13y equal to 0. And we have the roots 2 plus 3i and 2 minus 3i. So the real part is 2, which is e raised to 2x here, then c1 cos 3x and c2 sin 3x. We have other examples also. Let us find the solution of this differential equation, third derivative of y plus y equal to 0. For our kind information, I put here the nature of the roots. The roots are not equal and real, then this is the solution. When roots are equal, then this is the solution. When roots are the complex, I forgot to write I here, this is alpha plus or minus I beta, then it is e raised to alpha x, this, right, and c1 and c2 are real numbers. Okay, so now let us solve this example. Y triple dash third derivative of y plus y equal to 0. So here we have, this is d cube plus 1 into y equal to 0. Now you know how could I write d cube plus 1 into y. The third derivative represents d cube y. This is plus y. I took y common. Once y is non-zero, therefore d cube plus 1 equal to 0. You know which are the factors of d cube plus 1? It is d plus 1 into d square minus d plus 1. So either this is 0 or this is 0. We are not going to solve these two. I mentioned direct the roots. D is equal to minus 1 and 1 upon 2 plus or minus, actually this is complex entry, 1 upon 2 plus or minus I square root 3 divided by 2. Okay, so here we have three values. This is real, which is distinct from these two, right? These are two roots, 1 upon 2 plus or minus I square root 3 by 2 and 1 upon 2 minus I square root 3 by 2. So for this, we have e raised to minus 1 into x. See, e raised to minus 1 into x. Just try to understand. The number of examples are on the way. So easily we can understand. See, this is the real part, and real part becomes the power of exponential. So we have e raised to 1 upon 2 into x. I mentioned the roots with red colored, minus 1, which will be here. This is the real part, which will be here. And imaginary part is this square root 3 divided by 2. So which becomes c1 cos square root 3 by 2x plus c2 sine square root 3 by 2x. See, cos and sine. How do we write the constants? c1, c2 and c3. So this is one function. Let us multiply by c1. This is the another function, e raised to 1 upon 2x into cos. So we multiply by c2. This is the third function, e raised to 1 upon 2x into sine square root 3 by 2x. We multiply by c3. So we have c1 e raised to minus x plus c2 into this plus c3 into this, where c1, c2 and c3 are real numbers. So this is the solution of this differential equation. The next example, third derivative of y minus 3 into first derivative of y minus 2y equal to 0. Now you know what will be the auxiliary equation. D cube, that is because of the third derivative, minus 3 d raised to 1 because of the first derivative, minus 2 equal to 0. Yes, d cube minus 3d minus 2 equal to 0. This is the auxiliary equation. Okay, now let us factorize this thing. Can you try? D cube minus 3d minus 2 equal to 0, which has factors d minus 2 into d square plus 2d plus 1 equal to 0. You know how do we factorize this polynomial, right? D square plus 2d plus 1 is d plus 1 whole square. So this has three roots, 2, minus 1 and minus 1. All the roots are real. That means we are only in these two cases. case number 1 and case number 2. When unequal roots we have, then we apply this case. When equal roots, then we apply this case. So the final solution, e raised to minus 1x. Again we have e raised to minus 1x and we have e raised to 2x. Right. So because in real part we have this thing e raised to m1x, e raised to m2x, e raised to m1x, e raised to m2x. Right. Actually there is no x here. This is only c1 e raised to m1x plus c2 e raised to m2x. Now observe this thing, e raised to minus x, e raised to minus x and e raised to 2x. So here these two functions are equal, but I want that all the functions must be linearly independent. This time we have no idea about linearly independentness. Again I repeat the thing. In the next lecture we shall discuss what will be the linearly independentness for the functions. So what I do, these two functions e raised to minus x and e raised to minus x, I multiply by x here. Then these two functions are different. So I multiply by x. Then just multiply by random constant c1, c2 and c3. These three are arbitrary constants and this will be the solution. The next example, the differential equation d raised to 4 minus 1 into y equal to 0. So here, see here we have given the differential equation in terms of d itself, which makes our task very much easy. The auxiliary equation is this d raised to 4 minus 1 equal to 0. How do you factorize this thing? This is d square whole square. So this is d square minus 1, d square plus 1. This has the roots d minus 1, d plus 1, and this has factors d minus I, d plus I. So we have four values, 1, minus 1, I and minus I. These two are real numbers. This case, because they are distinct, please don't consider this x. Again I repeat, this is the mistake here. c1 e raised to m1x plus c2 e raised to m2x, this is only. These two are complex, I and minus I. So this is the case, alpha plus or minus I times beta. What is the real part and what is the imaginary part? So the real part is 0, because I can rewrite I as 0 plus I into 1, minus I is 0 minus I into 1. So the real part is 0. This is our alpha. Okay. So for real roots, minus 1 and 1, in the solution format, we have e raised to minus 1x. This is 1. So we have e raised to 1x. Real part is 0. So it becomes e raised to 0 into x. We have e raised to 0x. Now for cos beta x, sin beta x. What is beta? Beta is equal to 1 here. So it is cos 1x plus sin 1x. Are these functions different? Yes, this is e raised to minus x, which is different from e raised to x. These two are different from cos x and sin x. Right. So let us now multiply by the constant. Here we have one constant for this function, another constant for this function, two more constants for these two functions. So let us multiply by the constants c1, c2, c3 and c4. So this is the solution for the differential equation d raised to 4 minus 1 into y equal to 0. The next example, fourth derivative of y plus 4 times third derivative of y plus 6 times second derivative of y plus 4 times first derivative of y plus y equal to 0. What will be the auxiliary equation? D raised to 4 plus 4d cube plus 6d square plus 4d plus 1 equal to 0, which has the roots 1, 1, 1 and 1. Here I mentioned the roots of this differential equation direct. You can prove that d plus 1 raised to 4 is this. So it has the solution. Actually, these are minus ones, not ones. D is equal to minus 1, minus 1, minus 1, and minus 1. Okay. So the solution, how do we write the solution? For this real number, we have e raised to 1x. For this real number, we have again e raised to 1x. For this real number, we have e raised to 1x. And for this real number, again we have e raised to 1x. Now look at these four functions. All these functions are equal, but all the functions must be linearly independent. So equal functions are not working. So let us make these two functions unequal by multiplying x. So now these two functions are different. Generally, we use x, x square, x cube, only polynomials, right, to make or to convert the function into the linearly independent functions. Now what happens if I multiply by x here, then these two functions are equal. So I choose x square here, right? So e raised to x e raised to x square e raised to x. These three are different functions now. This e raised to x is same as this. So let us multiply by x, but then this is same as this. Let us multiply by x square. So it is same as this. So now let us multiply by x cube. Right. So I mean when the repetitions occurs, we choose x, then x square, then x cube, x raised to 4, x raised to 5, x raised to 6 as our requirements for the roots. This is for only equal roots. For imaginary roots, we have the separate quantity that you know, e raised to alpha x plus c1 cos beta x plus c2 sin beta x, right? Now these four functions we have, let us multiply by the four constants c1, c2, c3 and c4, where c1, c2, c3, c4 are real numbers. Okay, I hope so the idea is clear. Now let me discuss again the same thing. Three cases we have discussed. When the roots are real and distinct, then we have e raised to m1x and e raised to m2x. These two functions we have. When the roots are equal, then to make the linearly independent function, we multiply by x. And when we have the complex roots alpha plus I beta, then the real part becomes the power of exponential e raised to alpha x, and then the imaginary part will be in the trigonometric function c1 cos beta x plus c2 sin beta x. In the next lecture, we shall continue this thing. You just do practice with the different examples. Yes, I made a few mistakes. It was just typo mistake in this session. For example, here we have the roots minus 1, minus 1, minus 1 and minus 1. So the corresponding we have minus, 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 minus here. I forgot to write the complex number I in the complex root alpha plus or minus I beta. Right, next time I shall be more careful about the typing of this content. In the next lecture, we shall discuss how do we find the particular integral. Okay, thank you.